In Chapter 3, we've learned a lot of rules. And maybe for once we're pretty happy about that, because these rules that we've learned prevent us from having to compute the limit to find a derivative. So it really reduces the amount of work that we have to do to calculate something that's incredibly useful. For example, let's look at the function here, h of x. There's a lot going on here. I see a product between two functions, and then even within each of those functions that I'm multiplying together, I see compositions. So there's a lot going on here. Let's try and notate all of the things that are happening. We have a product between two functions, and then each of those functions that we're multiplying are compositions. So not only are we going to need the chain rule, we're also going to need the product rule. This is going to be a bit of a process, but be thankful that we're not using the limit definition of a derivative to find the derivative for this function, because whew, that would be way worse. So let's start by looking at each of these compositions as maybe a function called f. So let's let f of x be 2x plus 1 raised to the 5th power. We'll let g of x be 3x minus 2 to the 7th power. That means h of x is just a product of f times g. And that's going to help us see that we need the product rule, which would be f prime times g plus f times g prime. But then when we look at f prime, we notice that we need the chain rule. Because the f function is a composition. And the same thing when we calculate g prime, we need the chain rule. And that's because g is a composition of functions. So to find h prime, we need to find the derivative of that first factor. We're calling that f of x. And we need to multiply that to the second factor, g of x. Then we'll add to that the first factor, f of x, times the derivative of the second factor, g of x. So let's go ahead and compute each of the derivatives that we need. F prime is using the chain rule. So we're taking the derivative of the composition of functions 2x plus 1 and x to the 5th. X to the 5th is the outside function. So that function's derivative looks like 5x to the 4th power, but we need the inside function plugged back in. Then we multiply by the derivative of that inside function, which would just be 2. So f prime looks like 10 times 2x plus 1 raised to the 4th power. We also need g prime. G prime is the derivative of the second factor, which is the 3x minus 2 to the 7th power. That's a composition of functions. The 7th power is the outside function, so the derivative of x to the 7th would look like 7x to the 6th. But we need to plug the inside function back in, and then multiply by the derivative of the inside function. So g prime looks like 21 times 3x minus 2 to the 6th power. Now we can take those and plug them into our roadmap for h prime. So finally we have h prime equals f prime. times g of x. Now that's the original g of x, not the derivative, plus f of x, the original f of x, again, not the derivative here, times g prime. And that's technically it for the calculus. But of course, algebra doesn't want to lose the limelight, so we should get in the habit of cleaning up our work. Now technically, we found the derivative function, but for useful applications, it's going to be worth our time to try and factor this the best we can. Factored forms of derivatives are probably the heart of almost every derivative application problem. So let's practice factoring here. I see some common factors. For example, the 2x plus 1. I see my first term has 4 of those factors. My second term has 5 of them. I can pull out as many as they have in common. They both have 4, at least, in common, so I can factor off that 4. Doing that would leave behind 10 times 3x minus 2 to the 7th. And then in the second term, if I'm only allowed to factor off 4 of the 2x plus 1 factors, then one of them has to be left behind. Now we factored one common factor out, but that's not all of them, so let's go back and look for some more. I see that both terms inside of the larger set of parentheses contain the factor 3x minus 2. We have 7 of them in the first term, 6 of them in the second. We can factor out as many as they have in common, so we can actually factor out 6 of them. So I'll pull out 3x minus 2 to the 6th power. In the first term, that leaves behind 10 times 3x minus 2. One of those factors was left behind. And then in the second term, we are left with 2x plus 1 times 21. And at this point, the only thing left for us to do would be to clean up what's inside of the parentheses here, which is the same thing as 30x minus 20 plus 42x plus 21. Then we can combine our like terms here. We have 30x plus 42x. That looks like 72x. And we have a negative 20 and a positive 21. That would look like just plus 1. So although this first line that we have in white is the correct answer for the derivative, the factored answer is the best, because we can do a lot more with it. So it's good to start practicing all of that factoring now.